And so you can write UV, UV is B X, and B X inverse Y. Does that check out X inverse Y? Yep. If that's the case, or if we do have a Poisson map, it should be the case that this is true. Which is not quickly, but you can use Leibniz again. You're going to get X inverse, or X inverse F of XY. With this map, you get U inverse F of U X equal to U V. Okay, and locally, this would look like some U inverse. I mean, this is just around the point zero. We've blown up around the point 0, 0, but it would work for any P. V. And so we require that if we want to avoid any singularities, we require that F vanishes. Because G is holomorphic, or the locus of U is 0, and so we require that F vanishes. Or let me be a bit more clear. When I say U equals 0, I mean around the exceptional curve. And so if G is holomorphic around the exceptional curve, for the bracket UV to be holomorphic around the exceptional curve, we require that F vanishes. Or else we would get some problems here with this U inverse. Okay. So, in other words, just to summarize, for us to acquire another Poisson structure, or if there is a Poisson structure on the map that we have sort of blown down from, it has to be the case that it vanishes at the point that we have blown up. So our bracket pi must vanish at a point P, which we have blown up on our manifold. And that is all I've written down here. However, the idea with this is that you can sort of just keep on going down. Okay, I don't know how much I want to write because I haven't prepared this part, but I have read it. So just bear with me if I'm wrong. William, you can kind of shout or something. I don't know. But you can talk about what happens to the homology of these surfaces. And it turns out, I just said I wasn't going to write anything down, but it turns out that the homology of when you blow down, it decreases. And decreases in relation to the homology of the exceptional curve. And you can actually convince yourself that the process of blowing down does terminate at some point. And so that gives us a really nice way of classifying all of our Poisson structures on surfaces, because, well, what we can do is we could start with one surface which has a Poisson structure and just blow down. Okay, if I blow down and there's no Poisson structure, well, I can just keep on blowing down and blow down and blow down. There might not be one, but what ends up being the case is, so let me write down the homology stuff for you, William. Here. Use the blow up X with exceptional curve E. Then the homology groups of my blow up two and
Yeah, all of your exceptional curves, they all have the same topology, right? It's just
Yeah.
E1.
Yeah.
Yeah, that's where this E comes from.
Yeah. And, well, yeah, so.
This is just a connected sum. You're just doing a connected sum.
Yeah, and the thing is that you get that the, you can prove that the exceptional curve is a smooth rational curve, which tells you that it's isomorphic to P1. That's, yeah, how you can show that it's always P1. Just, yeah. Okay, so hold on. Yeah. So, yeah, I think, yeah, I guess we can just end. Well, I've said it in words, but I'll just write it for the YouTube. That we finish with the corollary of what we just showed. That X is a compact, complex surface. X tilde its blow up. This. It's blow up at a point for any Poisson structure on X tilde. There is a unique Poisson structure on X such that the map B is a Poisson map. This is the result for surfaces. And yeah, then this paper goes on to describe the complete classification, and I will not get into that because it talks about some very interesting surfaces. But however, they are the class 7 surfaces, Hopf surfaces, parabolic INOU surfaces, hyperbolic INOE surfaces, and intermediate Cato surfaces. Whatever those are. I mean, like I give you the paper, they sort of go on to it, like it's not too difficult, but all of them, they fit on a page, and all of them, all they do is they just talk about the divisors, the D that we were talking about earlier. Those are the ones with like different structures of their divisors, and they classify the Poisson surfaces, Poisson structures on surfaces. And in higher dimensional, open problem. Nobody knows. There's been some progress apparently by this guy actually, and I think what they want to do is he's quite reserved about it, but I overheard him talk about it in one of his lectures. It's something to do with, you just have to fix the notion, because now you're no longer, like, our divisors, D in our cases were these curves, but it's harder to work with higher dimensional structures now for divisors. Yeah, that's it. Any questions?
I have like a general question.
Yeah.
Why might a physicist care about this stuff?
Oh, probably no reason. I think for the most part, Poisson structure. Oh well, okay. I have to be really honest with you. This seminar concerns itself with the classification of with surfaces, so it probably has like no application whatsoever. Okay. Just the idea of classifying, I think, as a mathematical program, doesn't really have a lot of like applicable approaches to it. But like Poisson structures in general.
I guess even more general, like when you pass to like Poisson geometries, like a complex like category, homology category, is there any reason why physicists might care about it? Or are they just purely concerned with like real? Like,
good question. It probably fits into string theory. I'm not gonna lie.
That makes sense.
Physics that does like
Yeah, I mean, here, hold on. Actually, it's interesting you asked that. Literally on his first page, he's like, why might someone be interested? However, there are many situations, I'm just quoting the paper now. However, there are many situations in which one naturally encounters Poisson brackets that are holomorphic. So, the holomorphic setting. It's classical integrable system, moduli spaces in gauge theory, algebraic geometry, and low-dimensional topology. So I guess gauge theory. And classical integrable systems, too. Non-commutative ring theory, Lie theory, and geometric representation theory, cluster algebras, whatever that is, generalized complex geometry, and string theory.
I'd be interested to see the application of classical
Yeah,
systems.
yeah, that one was interesting.
Sounds like multipartite entanglement theory as well.
Is that true? Did we run into Poisson brackets?
Well, the other laundry list of stuff you read out, there's a lot of those turn up in
Oh, okay.
multipartite entanglement theory.
Okay.
Right, so if it's
Interesting.
relevant to them by sort of general principle of
Yep.
sensitivity, it's going
Yep.
to also be relevant to that.
Yeah, I mean, the big one, which is the one that I talked about in my first lecture, is you could talk about the quantization of surfaces. And a specific type of quantization is called deformation quantization, which has in its linear term a Poisson structure, or Poisson bracket, sorry. And so what you get is like if you take a surface, I was actually talking about this with the guy on Discord, Gio's Dawdle or whatever.
Previously,
Yeah, we were talking about this because I was telling him about my seminar. But like if you start with surfaces that perhaps like don't have a Poisson structure, they actually have like a very commutative product. It's, well, not very, it just has a commutative product, a nice product. You can deform it into something a little bit more funky, and that funkiness is described by the Poisson bracket. So it's definitely of interest to quantum field theorists, because their Poisson structures crop up just by nature of quantization. Yeah. Yeah. Any other? Yeah.
Could you go over again how this existence uniqueness argument works? Because like by the way you've set it up here,
Existence. Well, okay, wait, hold on. It's not unique. Remember?
you said there.
Oh,
unique, right?
you mean this stuff is? Oh,
Yeah.
Oh yeah, I thought you meant like because in the general case they're not unique. It's up to rescaling by a non-vanishing holomorphic function.
Okay.
So I'm sure what they meant by unique is that there just exists another structure over there that up to rescaling by some non-vanishing holomorphic function you'll get. Well, okay, hold on. Yeah, I think I'll stick with that. Yeah.
Yeah, because you're just asking if like the thing on X pulls back exactly to get the
To
thing on
yeah.
X.
So I might actually, I know it's in the paper, but I don't really like the word unique here. There just exists a Poisson structure on X, because we know that on X we can get more than one by just multiplying by some non-vanishing holomorphic function.
Okay, but the thing was that we needed the F to be 0 at the point. So how do we
Oh,
know
oh,
that
oh.
we can get that to happen?
Yeah, maybe it is unique then.
I still don't understand the uniqueness part, or the existence part. So like, how this argument works is like if there is something on X, then the local coordinates look like this.
Mhm.
And then we get a restriction, we get a constraint that says that F has to vanish at our blow-up point. But then what is the thing that we actually get? What is the answer that we get?
I don't know. I don't think I actually.
Is it this G? Is G the answer?
Well,
Like maybe I just don't get it.
yeah, I guess it is G. But no, I didn't actually read into like what the structure would look like. I just read that there exists a structure.
Okay.
So this paper's huge. It's like a 60-page paper, and it's very, very in-depth. And I've only gone, this is just 20 pages. But I do really want to keep on reading it, and it does talk about the uniqueness of substructures. And it boils down to something called minimal surfaces. Yeah. I'll send you the paper.
Okay.
But yeah, I also.
I mean, I can see the uniqueness being like such that B is a Poisson map, right? Because like it kind of restricts the blow up map. It like depends on the blow up map itself, I guess, right?
Well, the blow up map's the same for all of them. You just replace. I mean, the blow up map is. I mean, the inverse of this one. This should be blow down.
Yeah.
That should be blow down. If you meant blow down, then yeah, I agree. Yeah, the
Whatever
B.
the B is.
Yeah. And then that depends on your coordinates too, which is.
And yeah, just see if I understand the full picture, like So the reason you're doing the blow up thing or like the blow down thing,
Mhm.
you have the like singularity where like F vanishes thing. Is that
That's not why we do it. I mean, the motivation for the map is that we just wanted to see if it's possible to get a Poisson structure from one that we previously had. It just so happens that this construction with the blow up and blow down map, the Poisson bracket has to vanish on P. Does that make sense? It's not the fact that we like forced it to vanish on P. It was just that we created this map and it ends up.
you're not starting at a singular point,
No, we're not starting at a singular point.
just randomly.
A point, yeah, yeah.
Okay,
It could
okay.
be anything. That point itself could be singular.
Okay.
In which case you would just get that the vanishes on both. Or no, it doesn't vanish. One of them is singular and then the other one just vanishes, but no, doesn't have to.
So you're just starting with one structure,
Yeah,
making a bigger manifold
Yeah.
or whatever, and you get another structure.
yeah. Because again, like, if we have a structure if we have a Poisson structure, we can always just take local coordinates and morph it into a really nice thing, and it's only where around it's singular where we have to classify it. So what we can do is we can use this map, and then we could start to look at, okay, when is our Poisson bracket over there singular, and then we could start to explore what it looks like over there. Does that make a little bit more sense? Okay. Yeah. Also, I had a question. Is the recording done, or
Yeah, any other questions?
any other questions, or? Okay. What does this mean?
I can't see that.
Yeah, I know. I just realized. In the paper, they call it the